Okay, we are recording. Okay, good. So here's where we left off last time. Well, I hope everybody had a good break, by the way. Welcome back. Hope everybody had a good rest and relaxation. Per the announcement that I sent out somewhere along in there, don't forget we do have a midterm exam coming up on Friday, and so I hope everybody had some time to study, maybe a little bit during break. Anyway, reminder then as well, what we cover in class today is fair game for the midterm, for exam 2, right? But Wednesday, even though it's before the midterm, it's not fair game material because I don't think that's enough turnaround time. So anyway, there's that. Okay, so let's talk about where we were last time. We were doing symmetry theorems, and I basically restated this old single variable calculus theorem. It's a nice theorem. It doesn't get used terribly much in single variable. But anyway, what it says is if your integrand is odd and if your domain is symmetric, then your integral is 0. And you don't have to compute antiderivatives and use the fundamental theorem. You can just, boop, 0, end of story. Right? It's a really nice result in those few cases where that comes up. Okay, now why does this work? Why won't this erase? There we go. Why does this work? Here's a Riemann sum argument. The big idea is if you look at the terms in the Riemann sum, this term here at the reflected point and this term, this term here at the pre-reflected point, right? These are negatives of each other, and they're negatives of each other because of the oddness. Right? They pair up because of the symmetry. We know that any point over here has a corresponding reflected point reflecting over the origin because of the symmetry. And they cancel because of the oddness, because of that minus sign. So that's a nice, easy way to see it from a Riemann sum point of view. Now here is a different point of view, and that is to do a substitution. And recall, substitutions are just a single variable version of change of variables. Right? So when I say do this substitution, I'm going to kind of phrase it over here as, kind of from the point of view of change of variables as literally being a pullback. Right? X is a function of u, and plugging in accordingly and adjusting the domain accordingly, that integral is equal to this integral. Well, combined with the fact that our interval is its own reflection, because it's symmetric, and combined with the fact that the function is odd, and therefore that minus sign, nice little punchline, is that this integral is equal to the negative of itself. And what value could that possibly be that is its own negative? Well, only 0. Right? And so that's how we know that this theorem is true. That's that point of view on how to know that theorem is true. Okay. So we're going to now move on to doing a two-dimensional version of this. I'm just going to try to talk through, well, what would be the two-dimensional equivalent of everything that we just did in one dimension. We're going to start with the idea of reflection. Now, back here, we were kind of reflecting over the origin. Get some value p. The reflection is negative p, right? Just reflecting over the origin. A reflection in 2 dimensions, there's kind of more room to move, right? We've got 2 whole dimensions to play with, and you can reflect over various different lines. So a reflection through that line would be like so. Right? Is everybody happy with that? All right. With the idea of a reflection given, then we kind of piggyback and get ideas of, what is odd symmetry? Well, odd symmetry means that when you reflect the input, you get a negative of the output, just like in single variable. Right? And what does it mean to have a symmetric domain? Well, so again, there's different ways to say this. I think the easiest way to understand the idea of a symmetric domain is it's a domain that is its own reflection. This is one way to think about it. I've written it a little bit differently here, but take your pick. Okay, so analogous ideas, reflecting over lines instead of the origin. And we get, though, this very analogous theorem that I claim is actually really useful in lots of ways. If you have a odd integrand, you're integrating on a symmetric domain, then your integral is 0. So again, not only do you not have to do the anti-differentiating and stuff like that, you don't have to do the slicing, you don't have to worry about bounds, you don't have to worry about corners, right? Just you check these two conditions, boom, integral 0, you walk away. So, really nice theorem. Now, a couple of warnings I'm going to give. It is easy to screw this up. You do need to check both of these conditions. Merely having a symmetric domain doesn't do anything, right? It would be too much to ask, and you can come up with your own easy counterexamples when you have a symmetric domain, but not an odd integrand, and the integral will, of course, not be 0. Okay. Also, you do have to do these reflections over the same line. It's got to be the same line for both the oddness of the integrand and the symmetry of the domain. Otherwise, the argument's just not going to work. Okay. And you can kind of see where those requirements come in. Let me go down here to this picture. Here's my symmetric domain, my attempt to draw a symmetric domain. Notice it is its own reflection over that line, thus symmetry. Right. And that being the case, any term in the Riemann sum for the given integral, such as that one, will kind of pair up with a corresponding reflected term in the Riemann sum, such as that one. And because of the oddness, these are negatives of each other, and therefore everything cancels. All right, so analogous argument there. And then likewise, what I quickly skipped over previously, there is an analogous to the substitution argument, another pullback argument. Here I'm literally going to use the reflection as our change of variables. So this is literally just pulling back through the reflection and using all of our usual rules for pullbacks. And notice, again, I'm using the fact that the domain is its own reflection. That's the symmetry of the domain. I'm using the fact that the function is odd because reflecting the input negates the output. Right? And lo and behold, same deal, right? Just as we had before, we have that this integral is its own negative and therefore must equal to 0. So really, really analogous argument there. And by the way, this is why I like to put the section on symmetry in the section on change of variables, is because change of variables is arguably the slickest way to see this argument nice and quick. Okay. All right. So let's do one. Here is an integral to be computed. Now, you could brute force this integral. I think I can, at a casual glance, persuade you that that's not going to be a nice integral to do, brute force. Right? Just the algebra is starting to look a little scary there. Right? You see that e to the power of x squared plus 1. That's what I'm the most scared of there. But I claim it's even worse than that because you got to keep in mind the shape of the domain, right? The shape of the domain is bounded by these curves right here, which means that in your iterated integral, your y is going to be x squared minus x to the 4th, which means that that's eventually going to get plugged into there, which means your outside integral is going to be even worse, right? Is that good for everybody? All right, so this is a nightmarishly inconvenient integral. in reality. Okay, so now we have to be careful about this. You can't just make symmetry arguments just willy-nilly. We do need to think it through and make sure everything applies. So first, let's look at our domain. Quick drawing of our domain. Let's look at that curve first. X squared minus x to the fourth. Flashbacks to Calc 1, right? And curve sketching, and I claim that looks something like this. Yeah, ballpark, something like that. And then there's this curve, which of course is a lot easier. That's just that horizontal line like so. And geometric appeal from this picture, I'm going to suggest that the region that's bounded by these curves, namely this right here, is symmetric. Is that believable? Anybody willing to believe that? Okay. If you're not 100% clear on this, especially the purple curve, right? The purple curve is the one that's weirdest. It's the one that's a little hardest to kind of get your hands on. Since we're clearly making arguments about reflecting through over the y-axis, you can think directly about, well, what is the formula for reflecting, right? If I have a point there, and if I reflect, you get a point over here. What's that formula for that reflection? Well, you can see right from the picture that this point and its reflection, they're going to have the same y-coordinate, right? And the x-coordinate is going to be the negative of the original x-coordinate. So that reflection formula, again, just pretty geometric appeal, is going to be about like that. And so the idea of reflecting here amounts to, well, just stick a minus sign on the x-coordinate. That's what a reflection is in this context. And you can notice that putting minus signs on the x-coordinate, this purple equation turns into this right here, which, of course, a little bit of algebra, not hard to show, is actually still the exact same original equation, right? And so what that shows, this little argument down here shows that when you reflect this purple curve, it is its own reflection. Everybody willing to buy that? Now, here's the good news. Most of the time when you're making a symmetry argument, it's usually pretty clear from the picture if the domain is symmetric or not. So I don't require arguments of this sort on exams because they're always a little different, and it's just it's mostly an exercise in how to write things down as opposed to exercises in understanding of the ideas that we're sort of really most interested in this course. So you don't have to write down arguments justifying the symmetry of the domain. You do have to state the symmetry of the domain. The symmetry of the domain is a big condition. So you do have to actually recognize that you're using that by stating it. And you also have to be correct, right? So if you claim something's symmetric but it isn't, that's a problem. But you don't have to prove it. Okay, so let's see here. We've got a symmetric domain, and we just now need to demonstrate that the integrand is odd. By the way, we don't need our domain anymore. Let's look at our integrand. Here's our integrand, f, right? Well, I'll call f. How do we demonstrate oddness? What does it mean for a function to be odd? Well, reminder, for a function to be odd, reflecting the input has to result in a negative sign for the output. So here we go. There's the reflection. You can see I'm plugging in the reflection to the input. Now, here's where students sometimes get confused. How do we actually do this? How do I plug in this reflection? Well, keep in mind, negative x is what needs to go in for the first input to my function f. Negative x, therefore, has to go where x is in this expression. I'm going to put in negative x where x was. right? And then analogously, I'm going to plug in, let's see here, I'll use dark blue, y for the second input, which of course is just y. So y goes where y is, which, of course, nothing happens there. So there I've actually now plugged in negative x comma y into my integrand function, and I get this expression over here on the right. And now I've got to figure out what in the world am I going to do with that expression. And this is just some algebra. And, I'm going to leave the algebra to y'all. Y'all are good at algebra. But the punchline is that, yes, indeed, when you reflect the input, you negate the output. How's that? Y'all all right with that? Okay. Okay, so all right, we've been fiddling around at this point with understanding the domain and thinking about reflections and stuff like that. But I haven't done any integrals. I haven't done any slicing. I haven't applied the fundamental theorem of calculus or anything like that. And yet we are done. We have clearly shown that we have an odd integrand and a symmetric domain, and therefore our integral is 0 by symmetry, and we're done with this integral, right? There is no anti-differentiating. There's no slicing. We're done. Yes?
Is this something we should look for in every integral we do?
Yeah. It's top of my list. Yeah. Whenever I look at an integral, pretty much the very first thing that I do is I think, what's my domain? Is it symmetric? I hope it's symmetric, right? And then if it is, I think, integrand. What's my integrand? Is that odd? And I'm constantly on the lookout for this kind of thing. And that, by the way, thank you for that question, because that segues nicely into the next thing I wanted to mention, which is how often this is useful. And it's useful extremely often, as it turns out. I know a lot of y'all are engineers. I did not do engineering, but I did a second major in physics, and it's not that different. I have estimated, I've sat around and thought about, okay, how often did I really use symmetry arguments? And I'm saying that over my entire undergraduate physics major and the countless integrals that I did, I think about 20%, which is a lot, right? So there was 9 physics classes. That means 1.8 entire courses worth of integrals, 0 by symmetry. It's pretty awesome. So I think this is one of the most underappreciated, underpitched, underrepresented integration techniques. It is hugely important. It's extremely powerful, extremely convenient. It should be like its own section in the book, and it's more of a passing comment, unfortunately. Okay, so now that said, y'all know this is a class about reasoning and ideas. It's not a class about answers, right? So I want to directly and bluntly point out exactly what I consider to be a complete symmetry argument, and it requires 5 things to be done. You have to give me, what is your line of symmetry? There's lots of lines. That could be the line of symmetry you're talking about. You got to tell me what your line is. What is the formula for reflection through that line? We're going to need that formula for reflection, so you have to explicitly give it to me. You have to at least state for the record that the function is odd. You also have to demonstrate that the function is odd. And I want to point out, neither of these by itself is really sufficient. If you write down all of the algebra necessary to show that f is odd, but you don't come out and say, and therefore, right, then it's kind of spiking the football on the 2-yard line. You need to actually say that the function is odd also. And again, you have to doff the cap to recognize the importance of the domain being symmetric. You, of course, have to be correct about the domain being symmetric. You don't have to demonstrate that the domain is symmetric. Okay. So these are the 5 conditions. So on exam 2 anyway, if you want to use this symmetry theorem, you got to give me all 5 of these. Now, I do want to also give you a warning. This is just a heads up. I've seen a lot of this happen. This is very tragic when it does happen. And that is to be just really, really careful in using symmetry. So here's what can happen sometimes. A student, maybe a little careless about 5, right? And, makes a reasonable choice of a reflection line and demonstrates that the function is odd, but just doesn't think through carefully enough that the domain is symmetric. And then it turns out that it isn't. Domain's not symmetric. Well, here's the thing. If the domain's not symmetric, there is no symmetry argument to be made. Right? So progress toward a symmetry argument that isn't there is not progress toward a solution. It's progress toward a dead end. It doesn't go anywhere. It doesn't actually have anything to do with a valid solution of that problem. So if you're just a little too careless about it, and if you write down a bunch of stuff and oops, one of them, then you will be fooling yourself into believing that there's a symmetry argument that isn't there. Nothing that you've written down on the paper is actually progress toward a solution, and it's really, really hard in a situation like that to get partial credit because nothing is actual progress. So that's the danger. That's why this is a kind of a landmine situation. You got to be really, really careful. Please, please, please. I've seen this a million times. It's always heartbreaking when I see this. So make sure, don't go too quickly through a symmetry argument. Take your time. Make sure that it works. And then, of course, make sure to document. Yeah, question?
Is all you have to do to make sure it's symmetric, flip like the x's and see that it's the same?
What we did in this example, the reflection happened to be over the y-axis, and so the reflection formula was this. But if you reflect over a different line, there's going to be a different reflection formula. We'll see a bunch of examples coming up. Yeah. So once you've decided on your choice of line, then you do have to finish the whole argument. Yeah. Right. Okay. So heads up, be careful, dangerous, don't step on the landmine. Okay, this next example is just kind of a scoring example, just a heads up about how the exam grading is going to work. So here's a possible exam question, let's say, and then here is a hypothetical student response right here. Now, at a quick glance, you see the domain. Pretty easy to understand the domain. It's a little square, a unit square, right? And that's a symmetric thing. That's true. It is symmetric in more ways than one. So it's nicely symmetric. Great, cool. The integrand, x cubed minus y cubed, it does have an odd symmetry. This also is a true statement. And then you see symmetric domain, odd symmetry, and it's tempting to say integral 0 and, move along. But now let's just very carefully, and again, keeping in mind, it's not about the answer, it's about the argument. And is the argument sufficient? This student has observed that the function is odd, has observed that the domain is symmetric. This student never told me what line of symmetry they're using. Oh, what are we talking about? This domain is symmetric over 4 different lines. You got to tell me what line you're using. It's not a given. It's not clear. Right? This student has also has not indicated the formula for the reflection and claimed but didn't demonstrate that the function is odd. So as an argument, this is quite lacking. Right? It only did 2 of the 5 of the required steps. So this would be scored roughly proportionally to that. So again, make sure, give me the whole argument. That's what we're going to be interested in. Does that make sense to everybody? Questions? Okay, here's another example. This is a weirder one. So our domain is bounded by a couple of lines and this hyperbola. And, think through the lines. You draw it up, and this is what our domain ends up looking like. And again, you don't have to justify why the domain is symmetric. You just need to recognize that the domain is symmetric, and I'm claiming that through that line, the one I've got drawn right there, the domain is symmetric. So again, geometric appeal. I've stated it, and I'm right. Don't have to justify it. Okay, now how did I get this formula for the reflection? That is not immediately clear, so I'm going to come over to this little side page over here. Again, here's the line that we're using as our line of symmetry, and given a point x comma y, if I reflect, what's the coordinates for that reflected point? And notice this is pretty hard to see. Notice this is not just a minus sign. This is not minus x comma minus y. I'm not sort of rotating 180 degrees around the origin. It's not what this is, right? Points over here reflect to over here, right? So it's not just a multiply by minus 1. So how are we going to figure out that reflection formula? And there are different ways that you could go about doing this. I think the easiest way is to just notice that this rectangular frame is a lot easier to understand than the point that it connects to. So in particular, this little horizontal line, geometric appeal here now, that's a 45-degree line. Horizontal is going to reflect to vertical. Right? And then likewise, from there, this vertical line is going to reflect to horizontal. And so now I can read the formula for the reflection just right off of the page here. The first coordinate of my reflection, the horizontal coordinate of my reflection, I can see it right here. It's minus y. Right? And then the vertical coordinate of my reflection, again, I can see it right there. It's minus x. Everybody see that? It's a nice little hack. Right? This particular point of view when you're, is very handy when you're reflecting through 45-degree lines. Every scenario is a little different, but this is a nice tool in general, I think. Okay, so our reflection formula is, as previously noted, that reflection is given by that formula right there. Everybody happy? Okay. So now we need to worry about the integrand. We've got to make sure that integrand is odd. And okay, so again with the the thing that I'm plugging in for is that expression right there. That's my integrand. That needs to be odd. My reflection I've noted right there. Notice that's what I'm plugging in to my integrand. Again, you got to be real careful about this kind of thing, right? The first coordinate of what I need to plug into f, that first coordinate is minus y. That's going to have to go where the x's are in the original expression, right? So this minus y, first input goes where the first input goes. Likewise, the second input is minus x. That goes where the second input goes. The second input, and this original expression here is the y. So the minus x goes there and there. Is everybody on board? Does everybody see how that plugging in works? That's quite confusing. So you got to think that through slowly and carefully. Okay, so all of that noted. Then again, it's this matter of doing some algebra, and sure enough, as required, we do get this minus sign, and therefore, as required, the reflecting the input negates the output, and this is an odd function, and our integral is 0 by symmetry, and we walk away. Everybody happy? Okay. Okay, now what did this buy us? In this particular case, you could make the case that this integrand's a polynomial. It's not that bad. I mean, okay, 7th power, it's a little annoying, but it's polynomials. Could be worse. The thing that makes this really nice in this case is look how ugly the domain is. Corners. Right? No matter which way you slice, you're going to hit 2 corners. That means you're going to have to do 3 separate integrals if you do this the old-fashioned way. And that's not going to be convenient. And I think by any reasonable comparison, this is way better. Everybody good? Okay. Here's a landmine example. I've seen this kind of thing on student work on exams far too often, and that's why I make a big deal out of it. I think the bigger a deal I make out of it, the fewer students will actually step on this landmine. It's so tempting to look at this question and think, oh, hey, this domain, T, a triangle with corners in those locations, well, I can draw that, no problem. That triangle has corners there, there, and there. Hey, that's a symmetric domain. And then let's look at the integrand over here. The integrand is y cubed. I see the odd exponent right there. It's 3. That's odd exponent. So that's why we call this property odd, right? It's because it comes from odd powers among polynomials. So it's tempting to say symmetric domain, odd integrand, this integral is 0 by symmetry. And that's 100% wrong. It just doesn't work. Now, the domain is symmetric. You see it right there, but the domain is symmetric only over the y-axis. The integrand is odd, but the integrand is odd only if you're reflecting in such a way that y turns into minus y. In other words, only if you're reflecting over the x-axis. So what we have here are 2 different symmetry lines, right? The domain is symmetric through the y-axis. The integrand is odd through the x-axis. Different lines, no argument. There is no symmetry argument to be had here. Does that make sense to everybody? No odd symmetry argument. Okay, so heads up, please don't step on that landmine. I mean, by the way, not only would the argument not be valid, you wouldn't even get the right answer. Not that that's the point, but to whatever extent that might be persuasive, this integral isn't even 0. Right? Notice on the domain in question, y is always positive. This integral is not 0. This integral is some positive value. So there can't be an argument for it to be 0 if, in fact, it isn't 0. So, get the wrong answer. Okay, is everybody happy? All right. Okay, hopefully no surprise. You can do almost exactly the same thing in 3 dimensions. So in 3 dimensions, of course, we don't reflect through lines. We reflect through a plane. And the act of reflecting, it's just literally the act of looking in the mirror. Right? And so it's exactly what you think it is, as drawn in the picture there. And with this idea of a reflection, we can again write down basically the same definitions of odd symmetry and symmetry of a domain. A function is odd if reflecting the input negates the output. And a domain is symmetric if it is its own reflection, which I've written like so, but you can feel free to write it. And there's various different ways that you can equivalently. But again, I think the easiest, the most geometrically satisfying point of view, the domain is its own reflection. Okay, so with those definitions made, we have ourselves the exact same theorem. The exactly analogous theorem. This is a triple integral, of course. But exactly analogous in the sense that whenever you have an odd integrand and a symmetric domain, then the integral is 0. No slicing, no worrying about corners, no anti-differentiating, no various other related worries you have to deal with. It's just 0, end of story. So great result. Again, super useful. Bonkers useful. Again, do be careful. You have to have both conditions. One is nowhere near enough. It just doesn't. The argument crashes and burns if you don't have both of those conditions. And furthermore, they have to be in reference to the same plane for the argument to work as well. So do be careful about that. Okay, last example in this section. Let's compute this integral right here. Now, it doesn't look so bad at a quick glance. My integrand's a polynomial. No big. Right? Seems fine. But do keep in mind our domain is the problem. The domain here being the unit ball. What happens when you slice up the unit ball in rectangular coordinates? You get square roots all over your bounds. That means there's going to be square roots in your integrand. That means your integrals are going to be nightmares. Right, so this is a really, really hard integral if you want to do this in rectangular coordinates, the old-fashioned way. Now, you might be thinking, hey, spherical coordinates. I'll do this in spherical coordinates. And I think that'd be your best bet, frankly, without symmetry. So there's going to be a lot of trig, right? And not that we can't do trig integrals, but it's just going to be kind of a pain. Right? So I think even in spherical coordinates, this is no fun. Okay. All right. So here's the better argument using symmetry. Now, I am not going to present here exactly as the argument is written. I'm going to try to argue this in a way that exposes my rationale. Where did I pull this particular rabbit out of my hat? How did I know to do my symmetry argument through the xy plane? Pretty good question, right? After all, the unit ball, it has tons of planes of symmetry. Infinitely, any plane containing the origin is a plane of symmetry of that domain, right? So why did I choose the xy plane? So the reason why is because I was looking at this integrand and I saw this 3, right? And I thought, odd number, odd exponent, right? That's where symmetry awesomeness comes from, is odd exponents, right, among polynomials. So then I thought, okay, what kind of a reflection would allow me to capitalize on this odd power of z? Well, I would need a negative sign to go into where the z is so that negative would get cubed and remain negative, and therefore I have my oddness, right? So the fact that there is a cube on the z is why I wanted this to be my reflection. I want this minus sign from the reflection to go into there so that you can see how the algebra works out, right? I'm just trying to cleverly arrange for this to give me the minus sign that I need, just like here. So rewinding. I noticed the 3. That makes me want this to be my formula for my reflection. I emphasize this is a wish list. I don't know that this is a reflection yet. All I know is I wish this was a reflection. So now I have to ask myself, is this formula right here, in fact, a reflection at all? And if it is a reflection, what is it a reflection through? And so then you draw yourself a little picture. And let's see here. And if my reflection looks like this, well, then I am reflecting through the xy plane. Right? So if xyz keeps the same x and y, and the z just goes to the negative of what it had been, this is what my reflection looks like, and therefore the xy plane is my plane. And thus that. What do you think? Does that make sense? So this is just kind of strategizing, right? So this tells you how you can use an integrand to kind of reverse engineer a good choice. And then, of course, you do have to present the actual argument. We choose the plane. That gives us the reflection. And then, as you see down here in this algebra, this is how I know that my integrand is odd. And game over, 0 by symmetry. No nasty trig, no nasty radicals. Everybody happy? Okay. All right. So it's a great trick. Moving along to section 5.6. There's a bunch of applications in here. Holly does a really nice job in this section of motivating, kind of starting with a simple idea and generalizing just a little more and working up to a physics concept called center of mass. So I'm going to follow her process here. We'll start with just plain old, good old, regular old averaging numbers, which I know y'all know how to do. Here's an example of me averaging these 6 numbers. Right? So, yeah, but there's a point of view that says I'm kind of averaging 3 numbers. 4, 7, and 8 are the only actual numbers involved here, right? So it's 6 numbers, but there's really only kind of 3 of them in the sense that the 4, it counts twice, it contributes twice in the numerator. It also kind of contributes, you might say, 2 to the denominator. Right? And then likewise, which of course I can sort of summarize like that, likewise this 8 contributes 3 times in the numerator and it contributes a 3 in the denominator, which you can kind of summarize like that. And then I guess 7 appears once. We can write that like that. So what we'll notice is that all of these, all of these contributions really all kind of look like this. That looks like that. That also looks like that. And that also looks like that. Everybody see what I'm doing there? All right. Okay. All right. So now returning to, so this is let me say this. This is an alternative formula for how to compute a regular old, plain old, just average of, in this case, 6 numbers. Or you might think of it again as 3 numbers where some of them count more than others, right? So it's 4 counted twice because 4 is literally 2 of the 6 numbers that I'm averaging. And so I'm going to say 4 counts twice as much. We say that in this language down here as the weight of 4 is 2. And so in particular, the weights, these numbers right here, are 2 for the 4 number that's contributing, 1 for the 7, and 3 for the 8. So these 3 numbers, 4, 7, and 8, they have these weights, 2, 1, and 3. And so what we call the weighted average of these numbers, 4, 7, and 8, is given by this formula. So it's just kind of a reinterpretation of a regular average. The weights just tell you in some sense how many times do the numbers that we're averaging count. Everybody on board with that? Okay. All right. So having written this down now algebraically, we all of a sudden have a new flexibility that we kind of didn't really have when we were writing things down like this. Up here, it's I can count 4 twice. I can count 8 3 times. But what would it look like in this form if I wanted to count a number 2.5 times? I can't really. That doesn't make any sense, right? But having written it down like this, can I algebraically make sense of weights that are not integers? Yeah, sure. Just plug in not integers. It's fine. Right? So we've given ourselves this additional flexibility. The weights don't have to be counts. They can just be weights. They can just be numbers. So this next example, y'all might recognize is closely related to how we're going to do course averages, class grades in this class. Now, again, there's an explicit formula on the website, and I hope y'all have taken, a careful look at that and understand how it works. It is a weighted average, and so I'm going to be using this formula, like that. Expand it out like this to compute, Bob's weighted average in this hypothetical course. And it's going to go straight up by that formula. The weights, again, have been set for our course, and this is what they are for Bob's course. A little bit different. I didn't want the numbers to get too out of hand. So you can see those weights right there in the expression. And then you can furthermore see that Bob's grades, these numbers right here, are likewise right there where they're supposed to be, right next to the weights. And you punch up the arithmetic, and this is Bob's course average using the given weights. So the final exam counts more, right, than the midterms, and all of that in mind. This is how the arithmetic works out. Is everybody on board? Okay, so let's call it a weighted average. Now, real quick before we go on from that, I'm gonna point out that while we're talking about grades in this course, I do want to make sure everybody is comfortable with the formula for how grades are going to be computed in this class. So again, it's just a weighted average. The weights and all the other specifics are on the website. And so if you are not entirely clear on exactly what all that stuff means and how is your course grade going to be computed and what's the deal with the bins and stuff like that are on the website, come talk to me. I'll be very happy to discuss it as long as it takes for you to become comfortable with what that formula means. I don't want anybody not understanding how the course grade formula is going to work. So please just come let me know. Talk to me in office hours, after class, whatever. And I'll be happy to clarify. Okay, weighted average. Now, we're going to step it up in another way. This formula over here only works if you have a finite number of numbers to be averaged. What if you have infinitely many numbers to average, such as, for example, looking at the average value of a function over a certain interval? Well, for all of these values between A and B, there's infinitely many points on which this function takes infinitely many different values. How do you average infinitely many different things? And the answer is no big deal. You break it up into little subintervals, and as I've written here, you use size in the domain as the weights. So you'll recognize this structure right here as looking a lot like our previous formula, and I'm literally, for any given little subinterval of size dx, you can see I'm using this size dx as our weights. And again, we are averaging the values of the function. That's what we want to take an average of, and copycatting from above. There's our formula for the average value of a function. So it's a nice kind of generalization of the previous idea. Now, a little shortcut, you'll notice quickly that that's always equal to b minus a. And so if you'd like to, instead of using this as your general formula, if you'd like to use this as your general formula, yeah, okay, I mean, that's fine. In some sense, a little bit of the calculation we might as well streamline that, right? There's a point of view. So these are equivalent. The counter argument is that while this is maybe better for computation, because it's, again, slightly punched up already, right? This is better for relating to ideas that we've discussed previously. So this one is more intuitive. The left formula here is more intuitive. The right formula is, I guess computationally slightly easier. Anyway, I'm going to leave this as an exercise for y'all to count compute the average of that function. It's just a straight up integral. We're out of time, and we'll pick up here on Wednesday. Please do stick around for just a minute, and we'll do attendance.